from biology. This is called Arcane Theory. The idea is that there are species in a population of an environment that are selected for reproduction, things like rabbits and krill and plankton and so forth. They reproduce as quickly as possible. They have a short lifespan, many children. They have a minimal investment in their young. They breed randomly so that they have a diverse gene pool. They're very migratory. The death of an individual is considered a pretty minor loss. And then there are case-selected ones, which are things like whales, wolves, things that are large and are pretty much at the maximum capacity of an environment to support. Those are things like whales, trees, like I said. Much longer lifespan, much fewer children because they're already pretty much at the upper limit of the population. Strong defense of the young, strong pair bonds, strong gene pool, very territorial, and the death of an individual is a major loss. In engineering terms, we tend to think of things as cheap cell phones, tablet computers, and then on the case-selected thing, we tend to think of things as aircraft, especially fighter aircraft, space probes, anything with that kind of heavy investment in a very small population that is at the maximum carrying capacity of the budget as opposed to the environment. So in our metaphor, pawns would be R-selected, and kings, queens, rooks, and so forth would be more K-selected environments. So in our metaphor here, the royals would be the crew, would be the king, because if you lose the king, you lose the game. And then the queen would be the highly critical systems, such as the whole of the vessel and so forth. The rooks would be any mission-critical monolithic things. And our ships tend to be consistent of, okay, here's our life support system, here's our water processing system. They tend to be very monolithic in engineering endeavors. Then what if we break some of these down into small modules that can be rearranged quickly, they're more single function and so forth. So our chess game for Apollo, we have a very small playing set because it's a very small vehicle. We have, in the case of Apollo 13, we were able to castle. In other words, we were able to move the crew into the lunar module as lifeboats, and we were able to protect the king while the events were going on. And picture these opponent pieces as just moving at random. Somebody rolls dice and says, okay, that's my move, because it's not intentionally trying to kill you. In the case of the space station, we have more playing pieces because it's a much larger vehicle, but it's also, this is a 2-week mission as opposed to a 15-year mission. So under this metaphor and with our current engineering scheme, this is pretty much what a conventional Mars mission looks like. It's a lot of things trying to kill you in a very small resource base. Needless to say, this is not a game most people want to play. But what if we trade just one piece and we just replace it with a ton of pawns? Then, even if the pawns are moving randomly and these pieces are moving randomly, you still got a living shot at it. And each of those pawns is incredibly cheap, both from an engineering standpoint and from a financial standpoint. So we're getting away from this overemphasis on monolithic systems. We're not doing the poker game anymore. We're doing a much more level playing field. We're not going into bankruptcy trying to bankroll this sort of system. We break up the systems as tightly as we can. We stratify things that these things have to be perfect. These things don't have to be perfect immediately. We can reconfigure them. We make systems that can be improved in flight. We're going to get there. Because we don't necessarily think that we're going to get everything right the first time. What if the engineers on board the ship or working with the crew on the ground, it's like, oh, we didn't quite get the output of this system right, let's just rejigger a little bit. We can aggressively define the problem based on recent advances in theoretical physics. I'll get to there in a little bit to deal with the cosmic rays. So if we take everything from that column that was over there and move it over here, so we identify the systems, we categorize them into some pieces that can be broken down, we identify the radiation issues with each module, and we make affordable prototypes. So, good candidates for pawns, power management, lithium batteries, etc. Air processing, we can make a nice stack there, we'll get there. Gray water processing, food and medication storage, waste storage, tools, science gear, clothing, whatever. Smaller appliances, things like flashlights and so forth. And this is our pawn. Basically, the idea is that it's a hexagonal piece that can be stacked into a set of modules. You would have a compressible end on it so that you don't have to take apart the whole stack to get to something. You can just sort of squeeze it down and pull it out. You have standard ports for air, water, data, power. They are not, you don't have all those ports on all the modules, but you have an arrangement where you know where those ports are going to be when you have to bypass something through. For example, a power port, like a battery, you may have a hot, a positive and negative lead, but you've got 4 bypasses on the other 4 corners. So you just put a module in if you need to connect it in series, put it in directly if you need to connect it in parallel, rotate it 60 degrees. So those are the feature sets we were going through. Oh, service doors on the sides, so you can just pop open the entire thing, pull the guts out, and go for it. So here's a air processing system. You'd have a HEPA filter module, fan module, which is behind the HEPA filter module because you don't want to listen to those fans 24/7. Trace contaminant removal, post-fire recovery, which hopefully you won't use, but it's there, and if you need to use it and take it out, then swap a new one in. CO2 removal, which would link into a rail on the back, which would be for CO2 storage or removal and venting or whatever. We'll get there. Air quality monitoring, oxygen and nitrogen inputs, temperature and humidity control. So any water pulled out or water put in, you do it there. Bulk gas monitoring because you want to make sure that everything comes out of the system correctly and not to the vents. And all this would just be a stack of Legos in a series. Or you could take it around and do a 90-degree bend or stack them this way. It really doesn't matter. So if you take the Cygnus capsule like they're proposing for Inspiration Mars and you cover the entire sidewall with these modules, yeah, that's not a lot of space to be playing with. You'd probably pack the entire end cap with it with water storage and so forth. The modules on the outside would be less frequently accessed components, things like water storage, things like that. On the inside edge, those would be the things that you need to interact with relatively frequently. Things like, oh, I need to change this filter, or I need to do something like that. This is a hexagonal thing we'll be talking about tomorrow. This is the same unit and the thing plugged in it. This is a 6-foot person for scale, so you can tell these are fairly tight confines, but it gives you a way to maneuver things around. This would be more of a storm shelter than the actual vehicle proper. Something interesting happened with the Voyager probes. When Voyager was originally launched, they only thought they'd get back about 24 images from Neptune had they never changed the software and had they never changed the ground stations. But in the process of the 12 years it took to get out there, they upgraded the data compression software on the probe remotely, and they upgraded the receiving antennas. So we got about, I believe, 10 times that by the time we got to Neptune, in terms of the bandwidth. It's been done also on Cassini, when Galileo had the stuck antenna, they came up with new data compression algorithms, and they got most of the data back out of the mission. So what happens with these missions is the software tends to get better, even as the hardware, rust never sleeps. This will tend to degrade over time. So even though it was launched at this capacity, it actually goes up for a while until the hardware catches up to the software. However, when we take this strategy, our software will improve. In this model, the royals are degrading by 5% per year, in other words, the structure of the vehicle. The brooks are the things like the toilets and everything. Those are things that are not as critical as the whole of the ship, but not able to be modularized. Those are degrading 10% a year. But the pawns, because we can go in and say, oh, this is wrong, let's move this around, let's take 2 of these things and reconfigure them. You've given the crew something to do when you're going 180 days to Mars and back. But you're constantly improving these modules to where the ship may actually be better off 3 years later than it was when it was originally launched. Now on to the cosmic radiation. There seems to be 2 approaches to this. One is the, suck it up and take it and just go for it and just have minimal shielding. The opposite approach is, oh my God, the universe is trying to kill us, let's stay home. Neither of these approaches is particularly scientific or good engineering or anything like that. The things that are really, really nasty, down here in the very high energy, this is basically the dosage. I'm sorry, This is the energy level going higher and higher, and this is the dosage going higher, frequency. So this is what cosmic rays tend to do. But so every square meter per second is getting this really low dosage. This is the solar flux coming off the sun. This is the more common galactic cosmic rays. These are the extragalactic cosmic rays. When you get out here, it's about a meter, every square meter per year gets hit. Every square kilometer per year gets hit down here. I'm not real worried about this one. This is out of scope as far as I'm concerned. But the question is, how far can you push that back? And if I make a shield, how effective is that shield at slicing off layers of this attack? So originally, when you did particle collisions, the other nice thing about cosmic rays is when you start getting up into these power ranges, you're talking about something that is subatomic yet hits with the force of a baseball at 50 miles an hour. Now, that doesn't sound too bad until you put a needle in front of that baseball and think of it going through your body and everything else in the ship. Then it becomes a little bit more hazardous. But they're also moving at energies that are, I believe it's double or 10 times. When you get down in here, it's like 10 times the ability of a Large Hadron Collider to simulate. So the Large Hadron Collider is somewhere back in here. So we can't even simulate this on the ground. Now, something the nice particle physicists, theoretical people have come up with originally was things like Feynman equations, which model things where how a particle would come in and separate out the gluons and so forth at the nuclear level or subnuclear. That was recently replaced by the idea of a single-page calculation that could almost be done by hand called an amplihedron. Now, I don't know how well this applies to this problem, but the fact that we've taken the most complex thing that would normally take thousands of pages of equations and have gotten it down to a single page in the last year or so is a pretty impressive thing. Beyond that, you've got things like subatomic, ionizing, kinetic, thermodynamic. All those things are relatively simple to model. And the other thing that's happened, so if we want to take the original radiation dose, we've got the primary radiation, we've got the secondary where something hits something else and suddenly you've got protons in the equation and they're causing issues and so forth. Then we've got secondary radiation that has its own danger, and then you've got any primary radiation that came through there, and then eventually you've got the food, the medication, everything, and then eventually the crew. How do you model that when you've got such a very thin layer? Well, what we could do is video cards have actually advanced faster than Moore's law, and those are used very much for ray tracing. It's instead of tracing photons for, okay, I'm sending light through this glass and off this reflection and so forth. What if we use that same technology for modeling cosmic rays? So we have our cosmic ray model, which is more improved than the graph I showed you originally was from about 5 years ago. Since then, Mars Science Laboratory has given the environment from Earth to Mars and from the surface of Mars, and the advanced, or the alpha magnetic spectrometer has given a really, really good data set off the space station, so we have a really good low Earth orbit observatory of cosmic rays. So we have all this new baseline data. We have data on the mission. How many crew members do we have? What is our orbit? On the Holman transfer, are we going to be, at this distance from the sun or whatever distance from the star? What's our exposure time and so forth? And then because these units are modular, we have a very strong CAD model of, okay, for this module, how much carbon, how much oxygen, how much hydrogen, what is in that actual piece. So we've broken everything into, for lack of a better word, voxels, like in Minecraft. We've broken everything into single pieces that can be rearranged pretty much, maybe not quite at will, but into thousands and thousands of possibilities. And we can find the most optimal configuration for a system, where we're doing the nuclear model, the atomic model, the nuclear chemical model. And then eventually, after we get through all this with ray trace models, and eventually down to volumetric, okay, here's the human body. This is the ultimate target we're worried about. There's a little 1 cubic centimeter piece of the brain called the hypothalamus, which allows me to make long-term, short-term memory connections. I'm really worried about that. Here's my fingertip, same volume, not as big a problem. Okay, I've got 2 crew members. That means I have 2 hypothalamuses with 2 cubic centimeters inside this volume that I'm now modeling for. Suddenly everything, down to the organ, down to the tissue, down to the, okay, this is a food supply thing that it tends to degrade in nutrition at a certain speed because of the exposure to radiation, and certain radiation makes it lose nutritional value worse than others, etc. So we're not doing basic things of, okay, we're going to put all the human waste on the outside of the vehicle and then all the water and then all this. We're modeling everything in incredible detail, even on something as simple as Inspiration Mars. And then we can take these models and move them out into much more complicated vehicles. And we're iterating like this. So if we have these models ahead of time, and we have this sort of, okay, we've modeled that, we've said this is the risk factors for that sort of thing. Now we change the modules around and we feed it back through the system again. If I'm on this end, that's a really nice video game for kids to be able to rearrange the logo things, click things together and say, okay, run the test. They upload it to a server, it comes back, okay, your score is 97.3, I can do better. You've now crowdsourced the problem of the arrangement of the vehicle. And some 12-year-old could end up saving the life of the group. If you're a programmer, you understand this is kind of an object-oriented approach. We're breaking things into the right size Lego and we're arranging them in a certain pattern. This allows us to incredible versatility in design, which I'm pretty more gotten to. We can also prototype the cheapest systems first. We can focus on, if you're a company that makes really good air filters, you're not going to want to build a spaceship, but you could make an air filter module that's better than anybody else's air filter module. You've now democratized things to small business, to medium-scale businesses that want to expand into aerospace. You've dramatically increased the volume of the number of people working on a problem. You're essentially crowdsourcing all the way from top to bottom. So this has, these are the issues with conventional development, but if we go to a pond model, then everything is completely reversed. We've vastly simplified the radiation problem. We've vastly simplified the prototyping. We can create radiation models by module, and then just click the modules together and take the cumulative effects and so forth. And anyone who can build a module can be a player in this, whether it's somebody in the garage or whatever else. We can incrementally advance the technology so that CO2 filter in an original prototype might be just a disposable CO2 filter like they had on Apollo. But you can take a CO2 filter and put it in an oven and bake the CO2 out and then reuse it, which on a long-term mission would be pretty critical because you don't want to carry, 100 of these things. Now, as you do that, you may have, so let's say you put something in orbit, you have the disposable ones, and you want to test the other system. You would test it to destruction, go back to the disposable system, and fly back home at the end of your mission. Okay, what if I want Sabatier reactor? That's going to take up several modules. You're not going to be able to cram it down into a really small unit. But if it ever breaks, you've got a fallback and you've got another fallback. You can do CO2 removal cryogenically. You just freeze the air down to where it forms dry ice and you let the rest of the air through. You can experiment with that. You can use, if you want to vent it out to an algae tank or a greenhouse, you can do all that. All the other systems are working exactly the way they did before. So you can take every engineering challenge of the entire thing, scale up the technology, move into more advanced technology ranges without tearing apart the whole thing. You don't have to build a whole new vehicle or a whole new lab to test really advanced technologies. And as I mentioned, we can crowdsource the design work. We don't have only aerospace engineers working on things. We can have engineers in specific disciplines. Testing is not something where you need a special lab to do everything for 500 days, and if anything goes wrong, we have to tear it all apart and try it again. You can have anybody who can do anything with any piece of this, test it in the garage, say, hey, I've got a good idea here, send it off to a university, they can integrate it into whatever they're working on, and so on. Next versions are much more flattened out, and then we've got the computer module. It eventually becomes a gamification issue. This was originally part of a paper that went to a conference in Washington, D.C., where there were 4 authors and 7 pages. And obviously, I couldn't get this into my slot on the 7 pages, so I created this Kindle book. So if you're interested in more details about this, if you just look for Space Settlement Architecture with Mission Modules, or look on my name, Common Space, so you're not confusing me with a recording engineer on Van Halen Mountains in the 70s at the same name, then we're good to go. So thank you very much. Any questions?
there any application on Earth where something similar is used besides Legos?
We'll be talking about that in my second talk tomorrow.
Oh, okay.
But yeah, it's in a Mars analog habitat. It would be very easy to run a row of these things along the ceiling for power management. Or if you're just building a cabin and you're just a, you know, an off-grid resource company, and you want to, oh, I've got the solar panel and I've got these electric outlets, but I want to put something in between, build it modularly. On Earth, I would tend to want squares rather than hexagons because of volumetric issues. Like we tend to live in squares because we live in a gravity field and we don't have pressure differences. But other than that, exactly the same. Any other questions? Okay, 5 minutes, you're all back. Thanks.